So welcome to this lecture on 3D acquisition, and that is the art of measuring depth, measuring the 3D shapes of things in the world. Because the real world, of course, is three-dimensional, not like our two-dimensional image projections. And sometimes knowing about that third dimension, the distance to objects, is important. Like if you are building an autonomous car, you would really be interested in knowing where the car right in front of you is, how far it is. Or if you are driving a robot to grab the knob of a door, you'll also want to know the distance between the robot's hand and that knob. So the question is then, how do we get at 3D? And that is the topic of today, looking at different methods of doing so, of measuring 3D. This is a taxonomy of different methods, as you could put it together. And in this case we have made a distinction at the top, the purple things, between passive methods on the left and active methods on the right. Passive method meaning you just use normal ambient illumination. You don't do anything special with the lighting. And active techniques meaning you tinker with the illumination. So you may use a spatially modulated pattern that you project, maybe, or you do something with a sequence of different illuminations, so temporal modulation. Okay, below, both on the left and the right, we have a further distinction between unidirectional and multidirectional. And the distinction between these two is that unidirectional means only a single point of observation and or projection is involved, so a single vantage point, if you want. Whereas in the case of multidirectional methods, you use multiple vantage points. So you may observe from two different cameras, maybe, at different positions, or you may observe from one camera and project from a different position. And we will, of course, go through these different methods in more detail. Now, the first method that we want to deal with is stereo. And stereo is a method we humans are also used to, because of course we have a stereo system in our own head with our two eyes, because that is what stereo is about, using two cameras positioned at different places. So let's look at the mathematics behind stereo. To start our mathematical discussion, we have to understand what the basic principle underlying stereo actually is. And that is triangulation. You have it right up here. So our stereo system, as said, consists of two cameras. And here we have them. The camera on the left and the camera on the right. And each of the camera has their own image plane. So that would be the image plane of the first camera. And this is the image plane of the second camera. We also have a 3D scene. Here you go. And what we will now see is how to measure the 3D position of a certain point on this particle surface. Now, of course, we'll have, in reality, to measure the 3D position of many points, okay, of the entire surface probably. Okay, let's focus for a moment on that single point. Well, both cameras have it in their field of view, so both cameras see it. So that's the projection point to the left camera and this one to the right camera. Now, if the stereo system is completely calibrated, so we know all the external and internal parameters of both cameras, what we can do is, based on those two image projections, draw the corresponding projection lines. So if we have that point here, and we know where the camera is, the center of projection is somewhere here, we can draw this projection line in 3D. So from that image projection, basically. We can do the same for the camera on the right-hand side. So given this projection, we can draw that projection line. And the point in 3D is where both lines intersect. So as you have this kind of triangle with the base between the two cameras as one side and these two lines as the other two edges of the triangle. So that's triangulation. And by itself, it's a pretty simple operation. But by the way, and we will discuss that a little bit more in the coming minutes, but the big problem actually is finding these two corresponding points, because the assumption all the way has been these are two projections of the very same point in 3D. But how do we know that, right? So we have to solve this correspondence problem. But that has to wait until later. Okay, triangulation is the name of the game, and now let's look a little bit at what happens for different camera setups. And the first thing we will do is to look at a single stereo system with a simple setup. Here's that simple setup. So we have two cameras, one on the left and one on the right. Now, the centers of projection of these two cameras are here, that's the center of projection of the first camera, and here, center of projection of the second camera. Again, image planes are also drawn in this figure. That's the image plane for the camera on the left, and that is the image plane for the camera on the right. So then we apply triangulation. Suppose we know these two corresponding points here. So projections of the same point in 3D, then we can draw the two projection lines, see where we intersect, and that gives the 3D coordinates of our point. So that is what we're about to do now. Notice a number of special things characterizing this simple stereo setup. First, we see that we have two identical cameras actually, or we will assume to have two identical cameras. So all the internal parameters of the two cameras are identical. So same pixel sizes, same number of rows and columns, same focal length, f, that you see up there. Also the same. Second assumption, we have these coplanar image planes. So these two image planes are actually along the same three-dimensional plane. They are coplanar, as we would say. Notice that rows and columns of the two cameras are also parallel. So the x-axes are aligned. And actually, we go a step further. We also attach the world coordinate system to the left camera. So here we go for the world coordinate system. Here are the axes, capital X, capital Y, and capital Z. So these are the axes in terms of which the coordinates of this point X, Y, Z are expressed. And we assume, without a lot of generality actually, that that world coordinate system is fixed to the left camera. So the origin is at the center of projection of the left camera, and also the X and the Y axes are parallel to rows and columns of that camera. Now, the optical axis of the first camera is assumed to be the Z axis of the world coordinate system. That's also the place where we let row and columns numbering start in the left image. So the center of that image on the left is also the intersection of that optical axis with the image plane. Okay, so now we have to look at the projection equations as we saw them for cameras. So we start with looking again at the general equation. And here we go. So this is the projection equation for cameras that we saw during one of the previous lectures. So to remind you what's in here, you have P, that's the point in space we're looking at. So that is this point up here with coordinates X, Y, and Z. Then we have the center of projection of our camera. We have the orientation of the camera with respect to the world coordinate system, expressed by this rotation matrix R, and this is a transpose T. And then we have the calibration matrix of the camera. And if we calculate this expression here, we get the coordinates of the image projection for that camera, and that's written lowercase p here. And that's a 3 vector. Remember, we are using homogeneous coordinates here. So even if this is a point in a plane, it takes 3 coordinates because of homogeneous coordinates being used. And this being homogeneous coordinates also means it's all defined up to some non-zero arbitrary factor rho. Okay, now we have to specialize this for our particular setup as we find it up here. First thing to note is the world coordinate system, capital X, Y, and Z here, is locked in to the camera on the left. So the camera on the left has no rotation relative to that world coordinate system, meaning R, in our case, is the identity. So this R is an identity matrix. So it disappears, you can just drop it. But also the C's, the positions of the two cameras, the left camera and the right camera, are quite simple. Let's have a look. Here we are. These are the same projection equations, but now simplified for these two cameras. So first of all, you see there is no R anymore because that's the identity matrix as we just saw. Secondly, this is capital P. So that is the triple of space coordinates of our point. Again, here. And then we had minus C. Remember on the previous slide, minus C. C, the center of projection, the center of the camera. Now, where's the camera on the left? Well, it's positioned at 0, 0, 0. So here we have minus 0, minus 0, minus 0. So that also drops out. So that simple equation yields the image projection of our point onto the left camera. So we have lowercase x and y for that set of image coordinates. And then 1. As said, up to an unknown factor rho. Should not be 0, but the rest, it could take any value. Doesn't matter. It's all the same point. Same for the camera on the right. The camera on the right is pretty much the same. It has the same orientation. We assume it has the same calibration matrix. It's identical to the camera on the left. So this K is the same. The only difference basically is that this camera on the right has been shifted. It has been shifted with respect to the camera on the left over this distance B. B is called the baseline. So the center of projection of the second camera is now at B, 0, 0. And that's what you see here, minus C prime if you want, minus B, 0, 0. So almost the same, but not exactly the same projection equation. Then the calibration matrix itself. Well, here we go. We also simplify that a little bit. We assume there's actually no skew. We take it to be 0. That's not a wild assumption for modern cameras to make. And here, as the counting of rows and columns is supposed to start, here at this point, that point is the center of our cameras, in the intersection with their optical axes, we have no shift to the top left corner, for instance. So we have 0, 0 in the calibration matrix. Okay, so we have now two projection equations giving the two projections x and y for the camera on the left, x prime, y prime for the camera on the right. So now the question is whether we can go from the two image projections, from the coordinates locus x and y, and x prime, y prime, to the coordinates of the point in 3D, capital X, Y, and Z. And the answer is yes, we can. And in fact, we have to look at the small difference that exists between the two x's. So, as noted, the two y's are the same. So any point in 3D space will project at the same height in the two views, in left and right view, the same row if you want. But there is this horizontal shift. And that shift, x minus x prime, also called the disparity, that's where the information about the depth is. Okay, so here you go. It's a matter of calculation on an envelope to do these different calculations of x, y, and z. The most important formula on that slide, I would say, is the third here, because that's the actual depth from the camera that our point has. I know that z is found as a product of the baseline, the horizontal size of the pixel, and the focal length of the camera, but then divided by x minus x prime, this horizontal shift of the image projections in the two cameras. So x minus x prime, in this case, for this simple setup, is directly related to z. This is inverse proportional relation between the two. X minus x prime, the disparity governs this relation. Now, if x minus x prime, disparity is small, then following that relation, z must be very large. So that happens for objects at a large distance from the stereo setup. On the other hand, if a point would start to move closer and closer to your stereo system, the disparity would start to increase. So we can conclude that if you want to have a good, precise extraction of depth, that will work best for close-by points in stereo, because as the point moves further and further out, we have to depend on the disparity, x minus x prime, that gets smaller and smaller, so that we can measure with less and less of precision. Let's see what I mean. So on the left and the right hand side, we have these two stereo setups. So you have to imagine that we're looking from the top on a stereo system. So the centers of projection of the two cameras are found here, and here we are looking at the image plane, but from the top. So image plane for the left camera and image plane for the right camera if you want. Now, if we start to count pixels between this camera and that camera, the differences of pixels, we'll see that for the same disparities, we get all those intersections at a single depth for the same disparity. For instance, if you look at this camera here and focus on that point for a second, so if you focus on that point, we have, for the count in terms of pixels, 1, 2, 3, 4, 5, 6 for the camera on the left. For the camera on the right, this is the first pixel. So you could say 6 minus 1, that's 5. Now if you take the next intersection, that would be the 7th pixel for the left camera and the 2nd for the right. Again, difference x minus x prime, 7 minus 2, 5. And that goes for all those points. They have all the same disparity. And they are at the same depth. Now, if you look at other disparities, so this would now be a disparity that's slightly bigger. So that would be, we had before 5, so that would be like 4, 3, and so on. What you see is that, in fact, these planes of equal disparity are getting closer and closer to each other. So it's like sampling space more and more precisely as you come closer to the stereo setup. So at large distances, we are sampling the space quite crudely, and our precision accordingly is pretty low. But as you come closer, you start to sample more and more precisely. And in fact, disparity goes up for those planes. So what can we do about it? Well, in fact, we would like to measure with larger disparities. And if you go back a slide, you can see what we could do. So if you want to have now the same Z, but for a larger disparity, what you can do is take a larger baseline or a larger pixel size, but that will be very difficult because you have your fixed cameras here, so that is a no-go probably. Or you could also increase F, the focal length, to get the same Z for a larger disparity, for a larger x minus x prime, so that you can measure more precisely. So, we have these two options. We increase B or we increase F. Or, in fact, we could also increase both at the same time. And that's the difference between the figure on the left and the figure on the right. So the figure on the right is basically the same story. You have a stereo system, same pixel sizes, same focal lengths in this case, but we have increased the baseline. We have put the two cameras farther apart. And what you see is indeed that at a similar depth, you are starting to sample more precisely. These horizontal planes are coming closer to each other. But as so often in life, there are no free lunches. So there's also a price that we have to pay. And the price is that now points for which we could calculate the depth, because they were visible to both cameras, and that's a necessity, of course. If you have visibility to only one of two cameras, no way you can do stereo. You have to have the point projection in the two cameras. There are more points visible to these two cameras than those. And to have an idea, it's in fact all about this kind of cone that you see here, right? So points in this triangle here, they have a projection on both cameras. But that has shrunk, and now it's only like this. So more points only have a projection in only one camera. Their depth can no longer be calculated. Pretty much the same story if we don't go for the increase of the baseline, but rather an increase in the focal length. And here you go. Same story. That's again the very same image as we had on the previous slide on the left. And this again is a modified stereo system, where in this case we have increased the focal length. So the distance between center of projection and those planes here is bigger. Same story, we are for similar depth now sampling more precisely, so we are increasing the precision of our depth measurement, but unfortunately, again, there are more points that have a projection in the two cameras here than we would have here. So we lose a part of the space in which we can no longer measure depth at all. Finally, some remarks. First of all, what we just saw. So increasing B, N or F, baseline, N or focal length, will reduce simultaneous visibility. So we may get precision that is better, but on the other hand, we get less visibility. We notice that. Secondly, if you look at the places of points with the same parallax, the same disparity, you get these planes. So you get planes at different distances, each for different disparity values. That's only true for the simple setup. In general, that will not hold. So that direct connection between disparity and depth, unfortunately, is not preserved once we will go to the general setup, which we will do in a second. Third point, well, human vision is only precise up to about 10 meters. People sometimes overestimate what humans do in terms of depth perception with stereo. Beyond 10 meters, it's pretty much other cues that gives us a sense of depth. Occlusions, different parallax, different sizes also. So stereo works also for humans only up to some maximum, let's say about 10 meters. And finally, and I already hinted at that before, the real hard problem of stereo is to find the so-called correspondences. And that means to find the points in the two image planes that are projections of the same point in 3D. So we have to find these point pairs that are projections of the same point in the world. And this correspondence problem, that's the real hard nut to crack. Okay, here we have an example scene for a simple setup as we saw it. So we have these two mannequins against a planar background, and these are the two images. Okay, so these are the two images as seen by two cameras in this kind of simple setup as we have discussed. And this is the 3D reconstruction that our method has produced. And actually it's pretty okay. But of course it has been helped a lot. Because if you notice, the two mannequins have a lot of texture on the surface. And that texture helps to find unique patterns on the surface in the two images. So unique patterns are the same in the two images. So patterns that point at corresponding points. So in this case, the correspondence problem has been simplified a bit by having so much texture. And that is true in general. If you have good texture, usually stereo is of pretty good quality. But as soon as you have a textureless surface, a surface that lacks any texture like a blank white wall, you can almost like forget about stereo. Stereo will not work. So in this case, the system has actually been relatively clever because rather than doing something with the background, it knows I can't do it here. So it has left the background completely out. The best it could do because it cannot reconstruct the background. Any point on the background will look the same in the two images. So correspondences cannot be found for the wall in the background. Okay, now it's time to go for the more general setup, where we don't obey all these conditions that came with the simple stereo setup. And the first thing is showing a video that has been produced at a steel manufacturer plant in Belgium called Sidmar, close to Ghent. And this is a video.
Sidmar is a steel manufacturer situated at the North Sea coast of Belgium. It's a maritime integrated steelworks specialized in flat products. These include sheets, medium plates and heavy plates. Sidmar products are characterized by great added value, such as uniform mechanical properties, a carbon-free surface and good formability, ductility and weldability. As part of its continuous efforts to guarantee optimal quality and compliance with the customer specifications, Sidmar uses computer vision. Steel production starts with raw material handling. Coal is turned into cokes and iron ore is crunched. A blend of these is fed into the blast furnace to produce pig iron. At the steel plant, pig iron is converted into steel slabs or ingots. The hot rolling mill rolls them to a flat steel plate. Finally, in the cold rolling mill, the thickness of the strips is reduced further to anything between 0.15 and 3 millimeters. The vision system to be described operates in the hot rolling mill. The input of the hot rolling mill consists of slabs and ingots of several tons. Slab thickness is between 150 and 230 millimeters. The produced coils after hot rolling, on the other hand, have thicknesses between 1.25 and 12.7 millimeters. This reduction is realized in several stages. An initial thickness reduction of the slabs is realized in roughers. Further rolling of the material is carried out in the finishing mill. A process computer is directly linked to a mainframe computer. The process computer receives data of the rolling schedules from the mainframe computer and transmits the actual rolling results back. These data concern the achieved thickness and width of the strip as well as the exit temperature at the finishing mill. They're measured at different points in the hot rolling line. For the width measurements, several vision systems are installed, from Kelk and European electronic systems. One of the vision systems is positioned immediately after the last rougher and before the finishing mill, in order to assess the actual width and other critical parameters of the steel strip at that point. Readouts of the vision system are made available to the operators in the operator room. They include the evolution of the width along the strip, as well as its minimum, maximum and average values. Apart from assessing the evolution of strip width and its conformity to the specs, the vision system also yields indications for the crop shear on where to crop the head and tail ends of the plate. The optimal position depends on its further use. The crop is positioned after the vision system and just before the finishing mill. In the 6-stand finishing mill, the bar speed increases from stand to stand because of the decrease in plate thickness. Perfect synchronization has to be achieved in such a way as to keep the material flow constant between the different stands. The slightest tension on the material gives rise to a width constriction. After coiling, not shown here, the coils are transferred to the cold rolling mill. The vision system in the hot rolling mill continuously monitors the passing steel plates. As mentioned, it measures their thickness and determines optimal crop position. Here we focus on the width measurements. The vision system uses 2 linear CCD cameras of 2048 pixels. Each camera takes an overhead view of the steel plate. In this harsh environment, the cameras require cooling and monthly recalibration. The glowing steel yields a high contrast image. The grey level signal from one of the linear CCD cameras is shown on the oscilloscope screen. The plate edges clearly stand out. They are found as steep, dark bright and bright dark transitions. However, width as seen from an overhead camera no longer matches the true plate width if the plate is warped or bended. This explains the need for a second camera. Together, the stereo pair of cameras allow the determination of plate edge height above the supporting plane. This comes about through a procedure called triangulation. The projections of both edges are determined in both images. This suffices to reconstruct their three-dimensional position if the camera positions are known as shown. Actually, what matters are the differences in the edge positions, the so-called disparities. Being able to calculate the three-dimensional edge positions allows us to calculate the plate's width irrespective of warping or bending. In order to increase the accuracy of the measurements, one would like to make an optimal use of the camera resolution. Bringing the cameras closer to the plate has its limitations because edges will soon fall outside the images. A good solution is to tilt the cameras, in which case they can be brought closer to the plate. Upon inspection, the cameras in the vision system are seen to be tilted indeed. Vision has proved an important means to warrant high quality and customer satisfaction. Sidmar envisages additional vision systems for its cold rolling mills, where extremely fast yet sophisticated surface inspection is called for.
So, in the video we saw that sometimes there are reasons to not have the parallel cameras, to not have just the simple stereo setup. In fact, what we saw in the video was these two cameras were being tilted towards each other. So the orientation of the two cameras is quite different in that case. So now the question is, what can we do in a more general camera setup? Like this one. So here we have two cameras. They may be different in terms of their internal parameters. The positions are also more general than we had in a simple setup. These two image planes, for instance, image plane the one and this other camera, are certainly no longer coplanar. Now, in a simple setup, there was one important thing we knew, that corresponding points would be found on the same height, the same row in the left and right camera. And can't we find a similar constraint that would simplify finding corresponding points in this general setup? Indeed, we can again. And the whole concept that we'll introduce here are so-called apipolar lines. Let me show what we mean by that. So, here we have the setup. Suppose we have that point, we have the projection ray in the first camera, and now the point, the corresponding point, in the second camera has to lie on the projection of this ray onto the second image plane. So we don't know where exactly the point is along that line, along that projection of this line onto that image plane. So we could say where this camera sees this line, that's here. We don't know exactly where along the line the corresponding point lies, but it must be somewhere there. It can't be off the line. And that's important because now, instead of having to look for the corresponding point anywhere in this 2D image, we only have to look along a 1D line for the corresponding point. And that's a lot less work. Now, of course, that only works if you know where that line is. So now the problem is, given a point in the left image, what is the equation of this line in the other image? And that is what we are going to derive. This is the apipolar line, so-called, for that point. So first let's go back to the projection equations of the two cameras. Here we are. So we have this point in 3D, and then we have the image projections, lowercase p prime, for the two cameras. Two cameras with as image projection equations, these two equations. And now we have a general setup. So no more simplifications actually. You have two different cameras, different calibration matrices, possibly, K and K prime. We don't simply equate them anymore. These two cameras are also in general positions. There's no reason to fix the world coordinate system to one camera because the other has a different orientation anyway. So we have two different rotation matrices here. The same point that we consider in space, but the camera is also positioned at different positions C and C prime. Of course, that we had before as well. And that leads to these two image projections P and P prime, I said, with their factors. Because, again, homogeneous coordinates. Okay. So, now we have to look at the line that gives us the projection P. All the points that would lie on that line. So, we are actually looking at the projection ray for the first camera that has P as the projection, as intersection with the image plane. We know that if we project that line onto the second image plane, so if we see where the second camera sees that line, we have to have a corresponding point in that second image plane somewhere along that line. So the first thing is, what is the equation of the projection ray yielding P for the first camera? What are all the points yielding to that same projection P? And here you go. If you pull P out of this equation, this is what you get. Okay? So these are all the points in space, capital P, that would all project onto the same image point for camera 1, lowercase p. All these points, and there are multiple now because it's as if we start from C and we move out in the direction rk minus 1, that's the direction of the ray, of the projection ray of the first camera, a certain amount mu, because P is fixed, K is fixed, R is fixed, mu is variable. So this is the directional vector of the projection ray in the first camera. Okay, so this is actually the equation now of the projection ray for the first camera. Or in other words, all the points yielding the same projection P. By varying mu, we have different points P. Starting at the center of projection of the first camera. Alright, now the question is, where does the second camera see that line? So it's like we will plug in the projection equation for the second camera, all these points, okay? So we want to know where all these points along that ray, that projection ray of the first camera, are seen by that second camera. That is the epipolar line for point B in the second view. So okay, we plug this into this projection equation and we'll see what happens. Let me go quickly here. So, all right. So we have replaced that P by all the points on the equation of the projection ray for the first camera, and we get that equation now. So these are all the points P prime in the second image plane corresponding to points along the projection ray for the first camera, yielding projection lowercase p there. And we see, in fact, this equation has two components. On the one hand, this component here, and then also that one. And we will now analyze the meaning of these two components. Okay, we will start by taking this very same equation again at the top of the next slide. So there we go, that's what we had. Now, we start with the second term. This one, okay? So, in fact what we have here is a projection equation for the second camera, the one that we had before, like 2 slides ago or so. But now we don't have P minus C prime, we have C minus C prime. So basically what this equation gives us is the projection of the position of the first camera C on the image plane of the second camera. Or in other words, it's where the second camera sees the first, or the center of projection of the first camera. We call that the epipole, E prime. So this is an equation for where the second camera sees the first, or the center of projection of the first. The epipole, important concept in stereo. Now, then we are left with the first term and what that may mean. In fact, we will see that this corresponds to the projection of the ray's vanishing point, or point at infinity. So it's where the second camera sees the point at infinity of the projection ray of the first camera. And probably I best draw that. But before we go on, we can certainly say that if you look again at the details of that expression here, it is again the projection equation of the second camera, but now with Rk minus 1p instead of p minus c as we would have, or p minus c prime actually, as we would have in the expression of the second camera, the projection equation. Okay, and as we said, Rk minus 1p is actually the directional vector of the projection ray in the first camera. So it's like seeing not p minus c prime, but the directional vector. The question is, what projection into the second image plane is that? Okay, so let's consider the general setup. Here we have the image plane of the first camera. We have this image projection P. And then we have the central projection of that first camera, C. Right. Now the projection ray is a connection. That's the projection ray for the first camera. Here's the second camera. With its projection center C, let's say C prime. This is not a point in this plane, it's behind the plane. Okay, so the center of projection is not in the plane but outside, like here. It only looks a little bit inside here. And now we have to see how the projections of all the points along that ray look like in the second camera. That gives us the epipolar line in that second camera. So, a point here, maybe seen here, point here, right here, and so on and so forth. Okay, you would find all these corresponding points here. Forming actually the epipolar line. And we already know that this is a special point. It gives the epipole. It's where the second camera sees this point that we have the epipole. So that is more or less here. That's the epipole. Okay, that's E prime. Now, what is the other point? What's the first term? Well, we have to move out the point to infinity along that ray. Go out more and more and see how that projection evolves. And in the limit, we will have, in fact, a line starting from C prime and parallel to that image plane. And that line has this direction r k minus 1 p. If we draw that line parallel to this line, so here we have a line through that point parallel to that line, it's where this line intersects the second image plane that we have the first term, the projection of the vanishing point. And that may lie very far outside the physical image planes, the intersection of these two lines, okay, of the line that we have here with this line here. So in the end, it will reach a point corresponding to the projection, the point very, very far away along this projection ray onto the second image plane. And that's the first term. So it's a projection of the vanishing point of this ray. So let's continue. So I said what we have here is a projection of the second camera, but now instead of p minus c prime, we have this directional vector plugged into this equation, so replacing this difference. And that gives the first term, and it is the intersection of a line with this orientation, p minus c prime basically is an orientation vector, the line with that orientation where that has an intersection with the second image plane, and that is indeed the image of the plane at infinity of the ray in the first camera that happens to have that orientation. Okay, and that is the interpretation for these 2 points. So we have, on the one hand, this projection of the vanishing point and then the epipole. Now there's an important qualitative difference between the two. This first term depends on p. So if we choose a different p, a different point in the first image plane, the equation of that first term, or that expression, will be different. Not so for the second part. That has no dependency on p whatsoever. It's always the same. That also means that, in fact, if we take this line, you see we have the weight mu here, this is, in homogeneous coordinates, a line through the 2 points, this point on one hand, and then this point on the other hand, right? So depending on mu, we get all the points on the line connecting these 2 points, these 2 special points on the epipolar line. But that second term is always the same. So even if we choose a different point p, that line for a different p will again go through this point. So that epipole, and that makes it special, lies on all the epipolar lines in that second view. So whatever point we take in the first image plane, we get a line, an epipolar line, in the second image plane running through the epipole, always. Maybe one further note on that first term. We get this expression here with k prime, r prime, transpose, r, k, inverse. This whole expression is a 3 by 3 matrix again, because K is a 3 by 3 matrix, R prime also, so it's transposed as well. Then we have R, which is 3 by 3, and K's inverse are also 3 by 3s. So that entire product is a 3 by 3 matrix. We call that the infinity homography. And then we can summarize that lengthy equation here by this shortened version, but it means exactly the same. With A here, that infinity homography, so that product of 4 matrices, and then the apopole, E prime. And again, not dependent on P. Here, P is only here. Okay, so this is a summary of the apopolar line for a point P in the first camera. And that is a line connecting these 2 points. AP, the image of the vanishing point of the projection ray in the first camera in a second view, and E prime, where the second camera sees the first. Here graphically. And then it immediately is clear that indeed all these different apopolar lines have to run through the apopole. So we have the first camera, where the second camera sees the first, or the center of projection of the first camera, that is the apopole. But all the rays, independent of the point P that we choose in this view, run through that same center of projection. So we get this pencil of lines in the first camera. So even if you take another point P in the first image, you get the different projection ray, but all go to the center of projection here. So we see where the center of projection appears in the second view, that's the apopole, and all those projections, this entire pencil of lines of the first camera, project onto lines all intersecting at the apopole in the second view. And that's also what the mathematics says, right? That apopole runs through all the apopolar lines, whatever P projection in the first image you choose. So, it is very useful if we can calculate the equation of the apopolar line, because as said, it throws a 2D search for the corresponding point into a 1D search. Now the corresponding point for P has to lie along that one line, the apopolar line, in second view, and not just anywhere in the second image. Okay. So that's the summary again of the equation of the apopolar line, where we said it has 2 components. The first one, which is the projection of this vanishing point, containing P, because the vanishing point depends, of course, also on the direction of the projection ray in the first camera. And then we have this second component, E prime, the point all the apopolar lines in a second image go through. That is in fact the projection of the apex of that pencil of lines that we saw in the previous slide being projected onto the second camera. We can go a little bit further now in reformulating what we have. If you look at the first equation, this is a 3 vector, that is a 3 vector as well, and that's another 3 vector. So column vectors with 3 elements. And we see there is this linear dependency between the 3. That's expressed by this equation. There is this linear dependency between P prime, AP, and E prime. That means that these 3 vectors that live in a 3-dimensional space are dependent. So if you would calculate a volume with the 3 vectors as the vertices for the volume, for the parallel pipes that spans this volume, it would have to be 0. In fact, P prime has to lie in the plane spanned by E prime and AP. That's what that equation says. P prime has to lie in the plane spanned by AP and E prime in a three-dimensional space in which these three vectors all live. And that means if you take volume spanned by the three vectors, it's in fact squeezed flat, so it has no volume. This is the volume that would occur if you would have a body spanned by P prime, E prime and AP, only now P prime lies in the plane of E prime and AP. So that volume here is 0. By the way, this is a 3 by 3 matrix. The first column of that matrix is P prime, the second column is E prime, the third is AP. And then taking the determinant of that 3 by 3 matrix, that is the volume of this body spanned by P prime, E prime and AP. Another way of saying exactly the same, that P prime lies in the plane spanned by E prime and AP, is this equation here. Now, what does it say? Here we have a vectorial product of E prime and AP. So that's the normal to the plane spanned by E prime and AP. So that's if you have E prime and AP, the normal to that plane, that's what this vector is, a vectorial product. Now, we can project P prime onto that vector. So transposed because we make it a row vector, this is a column vector. We say, okay, there must be no component of P prime sticking out of the plane spanned by E prime and AP. Or in other words, P prime must lie completely in the plane spanned by E prime and AP. Nothing must stick out. So that's exactly the same meaning. Again, it has to be 0. So this equation can be reformulated like this being 0 or that being 0. And the reason why we are going through all these pains is because we want to end up with a very simple equation that summarizes epipolar geometry and that people use throughout the literature all the time. Namely, here we have this vectorial product of E prime and AP. It can be shown that if you multiply this vector to the left with this matrix, so you take this matrix multiplied with that vector, that's the same as forming this vectorial product. Again, something you can show pretty easily. Okay, so if we do that, we get the following. So that product is replaced by the product of this matrix, that's the matrix defined here, with this vector. So that's this vectorial product is also given by this matrix product of matrix and a vector. And then we still have the P prime transpose here as well. And that has to be 0, you know. Now, 3 by 3 matrix, 3 by 3 matrix. So we can multiply this matrix by that matrix, we get a 3 by 3 matrix. We call it F, the fundamental matrix. Fundamental because, yeah, that's the summary of epipolar geometry reappearing very, very often in papers about depth perception and depth measurement. So F is a product of 3 by 3 matrices, is itself also a 3 by 3 matrix. But it's not a general 3 by 3 matrix. It has to have rank 2, so that's an important constraint. And how to prove that? Well, you can see that actually the determinant of E prime x, this determinant of that matrix, vanishes. It's 0. So the determinant of that matrix is 0, therefore the determinant of the product of this matrix with another matrix is also 0. Because, as you know, the determinant of the product of two matrices is the product of the two determinants. And if one of the determinants is 0, so is the product, or determinant of the product. So F has a determinant 0. It has rank 2. It's rank deficient. It's maybe a 3 by 3 matrix, but it has only rank 2. So some comments. Maybe let's go back to the previous slide for a second here again. So what we get here is P prime transpose F, that's the new name we give this beast, P is 0, okay? So that's a summary of apopolar geometry. So, if you have a point in space and its two projections, P and P prime, corresponding points, projection of that point in the first and the second camera, we know that the two projections must satisfy this relation. Basically, it says that if you take P prime, it has to lie on the apipolar line of P. Because you have to understand that this equation indeed is expression of a straight line. If you take F, a 3 by 3 matrix, and P, a 3 by 1 matrix or 3 vector, that gives us a 3 vector again. And those are the line coordinates of the apipolar line on which P prime has to lie. No, by the way, this is highly symmetric. We will come back to that. Now, this is an equation for two corresponding points, P and P prime. So, in fact, that opens an interesting possibility, namely a way to get at F from pairs of corresponding points, P and P prime, if you would happen to know them. So far we have been calculating F with an entire set of steps, kind of forward calculations from external and internal camera parameters up to the definition of F. So that's one way of doing it. Of course, it has a big disadvantage that you have to first precisely calibrate your stereo setup. You have to know where the cameras are with respect to each other. You have to know the internal settings of the cameras. So you have to know K, R, C, everything. And then you can calculate F. A perfect valid way of doing it, but maybe a little bit tedious. If you're just given two images, you can always get at F as well, though, if you have a sufficient number of corresponding point pairs. Because it may happen that some points really stand out in the scene, so you easily find the projection of some of the points in the two views, because there's something very particular about that point. And if you have a number of such points, you have a number of corresponding point pairs, P and P prime, that you know in advance. Now, every point pair, P and P prime, yields one equation of the style that you have above. P prime transpose Fp is 0. One equation, not 3, 1. And that also means that you can calculate F if you would have knowledge of enough of these corresponding point pairs. Right? Then you can go after the elements of F, because every equation P prime transpose Fp is 0 is linear in the elements of F. So a nice simple equation. Now, so that opens the hope that from correspondences actually you can get F as well without knowing the camera parameters, external or internal, doesn't matter. How many point pairs would you have to use? Well, the answer is 8. Now you may think, that's strange because, you know, there are these 9 unknowns. F is this 3 by 3 matrix. So there are 9 elements in F. So I have to solve for 9 elements. Why wouldn't I have to know 9 corresponding point pairs? Well, the reason is that all these equations are homogeneous, right? So you have P prime transpose Fp is 0. So if you multiply all the elements of F with the same number, non-zero number, you basically get still all the same equations. So F is only determined up to some unknown scale factor. So you could put one of the non-zero elements of F to 1 and then calculate all the remaining 8 parameters relative to that one. So there are actually 8 degrees of freedom only, 8 unknowns. So 8 pairs of corresponding points are all you need to linearly go for F. Okay, actually the situation is slightly better if you also work a little bit harder. Indeed, there's one thing that we know about F but have not used yet, and that is F has rank 2. So we have an additional constraint on the elements of F. The determinant has to vanish. We have not thrown that into battle yet. And what that actually means is that you can take away one of the corresponding point pairs and the corresponding equation and replace that by the rank 2 condition. Determinant of F is 0. If you do that, you're left with the task of only finding 7 pairs of corresponding points. And you can still go after F when also demanding the rank of F to be 2. Unfortunately, that last equation of the rank being 2 is no longer linear in the elements of F. It is cubic. And that is because of the following reason. So let's look at reason why. Look what that equation determinant of F is 0 means. Let's say F is the following, the matrix I mean. So that would be F with its 9 elements. And now we say, oh, the determinant has to be 0. So we say determinant has to be 0 because we have this rank 2. What kind of an equation is this in the elements of F? Well, if you look at the expression for the determinant, it gets us to something like this. F11 times F22 times F33 plus F21, F23, F31 plus, and then minus, in total we have 6 of these terms, but they all contain a product. And by the way, that would again be 0, expression for the determinant. All the terms, if you develop this determinant into its minors and so on, all these terms contain 3 elements of F. They're all the product of 3 elements of F. So we have a cubic equation. So no longer a linear equation. We had linear equations before. We still have a linear equation for every pair of correspondences. Now we reduce from 8 to 7. Instead we add this equation, but it's cubic. So it's no longer linear. It's a bit more difficult. Now, in principle, you could do it with 7, which is the minimum. In practice, people tend to use more points that are potential corresponding pairs. And what you could do is go for a least square solution and then project onto the manifold of rank 2 matrices. That's one way of going. People often also use Ransack, a robust algorithm. and they start within 7 or 8 point correspondences until they find a good solution. We don't have time here to go through the Ramsack algorithm though.